Okay, so let me start. What is learning? So learning, I guess, is an informal term, and we're going to drill down and give a more formal interpretation of it, and then I'll start talking about the mathematics that might be associated to that. But to start with a dictionary definition, which we'll refine, learning could be said to be the acquisition of knowledge or skills through experience. Now that definition is a bit too broad, because you can take, say, experience to mean just acquiring information from the environment, right? So if somebody flips a coin and then tells you the result, that's information. And you could say you'd learned the outcome. That's a English phrase that wouldn't make people bat their eye. But that isn't really what we mean by learning in the present situation, right? That's just getting information. Now, if you were told it's a biased coin and you don't know the proportion of heads or tails, and you see many samples, that is, you get the results of many individual coin flips, each one of those coin flips is some information, and you would say that you're learning what the bias is over time. That is a proper use of the term learning in the sense we're going to mean it, but not the first. So learning and communication are not the same thing, although they're closely related, of course. And it's hard to imagine learning happening without some form of communication or information exchange within an environment. Now, you could also say that if you program a computer to play chess, that the computer has learned to play chess. That's also another informal usage of this word. But that's not the sense of learning that we really mean. Although you could have a computer learn to play chess, as we know from AlphaGo and AlphaZero and so on, and many systems before that. So there's a continuum of notions between somehow hard coding something and learning in the sense we're going to mean it. But we don't want to just conflate these two things. So learning is not the same thing as sort of programming. Although again, they're somewhat related. Okay, so here's the definition we're going to, still informal, but the definition we're going to use. So we're going to consider an agent. So this is the thing that does the learning in an environment. This is the place that the thing to be learned about lives, making measurements of, I'll say, computable process Q. So Q lives in the environment. It's generating some sort of signals that we can measure, receive as an agent. And I say computable because presuming that the agent somehow runs with bounded computation and can only manifest computable functions, then somehow a process out in the world that's not computable really is hard to imagine as subject to being able to be learned. But that's kind of a controversial point of discussion for later. So learning is the process of the agent searching for a model of Q, some part of the environment. What's a model? Well, once we get into more mathematics, we'll be more precise about this, but for the moment, I'm just going to say a model is an algorithm. That is, you can do something, you can expend work and compute predictions for what the process Q out there in the world will do, and then you can compare your predictions to the actual measurements, and you say that the model is true if it reproduces, at least in distribution, measurements from Q. Okay. Now I can take questions at this stage, but I'll start drilling down a bit more into what I mean. So we're going to assume...
Wait, so is Q something that is not necessarily a deterministic process?
That's right, yeah. For example, the biased coin flips. So the process, suppose it depends how you think about it. You could say the process is kind of like the generating mechanism behind the measurements that you observe, the events that you observe, or it is kind of the sequence of all possible measurements that might happen and also that do happen. I think it's better to think about it as the mechanism behind the measurements. So if the world was a simulation, it would be the code that is running that generates the measurements. And you're trying to infer what that underlying process is that explains the things you see. Please tell me if I'm standing in the wrong spot as a speaker. I'm trying to manage both the iPad and the recording and so on, so it's quite possible I'm getting it wrong. So we assume the possible models. So far there's no sort of geometry or even anything continuous necessarily, but we assume the possible models are parameterized by points of a space, which is going to always be called W. Now, learning was the process of finding or searching for a model, right? And if models are parameterized by points of a space, that means that learning is some kind of dynamical process on W, moving around on W. Each step is a model, looking for a model that is true. And here's my little sketch for, that's my head. Here's W. Here's some interesting thing in the environment. I make measurements, and maybe I start with a very bad model. I'll call that W1. And then I can steadily refine that model. Maybe the true model, I'll call it W star, lives down here. But just because I take measurements doesn't mean I instantly sort of know how to reconcile those measurements with my model, how to reproduce them with my model. Right, maybe I do, if it's a very simple model, and it's a very simple process. But generally, there's some process of sort of adjusting yourself to the information in order to align your model with the measurements, and that process is learning. At least in the sense I'm going to use it, the word. Okay, so W1, W2, W3, dot, 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 in some sense converging, hopefully, to W star. That is learning. So this is the truth. In the sense that if you were to plug W star, those numbers, into your algorithm, that is the model, it would produce predictions of measurements for Q that are exactly the same in distribution as Q itself. So this is the environment over here. Okay, so in that diagram, knowledge acquired by the agent, it's different to just the information of the measurements, right? And the difference is exactly the learning process. The information of the measurements, it just sits there on paper. That's not knowledge. Knowledge is the end result of this process of learning, whereby you reproduce the measurements, or at least in distribution do so, using the information that you obtain by searching for a model. Okay, so that's knowledge. Knowledge acquired by the agent is a parameter W star. Or since you never, well, except in very simple examples, you never probably actually really reach W star. So maybe knowledge is not a point, but it's the process by which you asymptotically approach the point. Or maybe even better, the gadget or computational device which, when work is expended on it, produces more accurate approximations. That's probably the best I can do. So is a parameter W star whose associated model correctly predicts Q.
Just a quick question.
Yeah.
Should I imagine that inside Q is like a secret point in this parameter space that's generating the things that are being measured?
To a first approximation, yes. But my next point is going to be that there may be multiple points in a space of parameters which predict exactly Q. So the point about computability is going in the direction of what in the technical language is called realizability, which is that, I mean, you could certainly imagine that your model is so stupid that no parameter actually reproduces Q, right? And certainly, you know, many very complicated processes out in the world can never be matched exactly by somehow a model that we'll ever be able to compute with. But assuming it is possible to precisely match it with a model, we do sort of have in mind that you've discovered the secret DNA behind that process by finding W star. That's right. Okay. So I'm going to give an example. In which we can see this process and we can see the point I just alluded to, which is that maybe multiple points in parameter space reproduce Q. And what would that mean? Okay, so let's consider a pendulum. And the measurements we make are the following kinds of pairs, x, y. Consisting of some initial angular displacement x. I'll draw a picture in a second. So here. Excuse me while I decrease the sum total of bitey organisms on the planet. Okay. So that's the length of my pendulum, 1 unit. There's a mass at the end, m. I'm going to call this angular displacement, I'll call it theta. So the forces at work on this pendulum are gravity. I assume that string tension cancels out the part that's parallel to this string, and so what's left is this mg sine theta. So many of you have done this exercise, probably all of you. Okay, so that's my system, Q. The measurements I'm making of it are the initial angular displacements, so the initial thetas. And I'm going to say we're certain about those, so we start the experiment at some angular displacement. And the other measurement we make is the angular displacement y after time t. And that's subject to measurement error, or I'll just call it noise, which we assume is normally distributed. Okay, so the probability that we measure angular displacement y, given we started at x and given the various parameters that are involved, so we assume these are fixed but perhaps not known. So that's a normal distribution by assumption with some mean f that depends on x, g, and t. Right, so we've got, this is theta. Here's the truth. That is, if you were to actually perform this experiment, this is where it would end up, or perhaps it's better to say that if you solve the equations of physics, this is where you would say that the pendulum must be after time t. Right. So that's an indication of the probability distribution that you'd actually sample from if you made the measurements. Okay, so here f is the sort of actual displacement according to Newton. Alright, so let me write down the actual formula for what F is. It's an exercise to do the physics if you wish. But it's interesting to see in the context of the story I'm about to tell what it looks like. So solving, so making the assumption theta is small is the usual way you do this, and you solve that dE and you'll find that F is given by the following formula. Oh, I forgot to add one slightly artificial wrinkle. Okay, so I'm assuming that there's initial velocity. So assuming initial angular velocity v0 that depends on the angular position. So that is, you give the pendulum a little bit of a push, and the magnitude of the push depends on how far away it is, and let's say for simplicity that it's proportional to x. Okay, so then you have this formula. I'll call that double star. I guess you can still see this on Occams, so I'll indulge myself and put a star over here as well for the distribution itself. Okay, what's the point of all this? We can attempt to estimate. I mean, what would it mean to predict future measurements? Well, we can solve the equations and we can get this formula, But we're given a list of x's and t's, right? The pendulum's swinging, and somebody's maybe it's in a different room, we're not allowed to mess with it, but somebody tells us the experimental setup and gives us a list of xg pairs. To predict new ones, well, one way we could do it is we could solve these equations and get this formula, because we know it's a pendulum, we know the laws of physics. But to compute this formula, we need to actually know what g, t, and lambda are. It's not enough just to have the x, right? Somebody tells you the x, or maybe there's an agreed upon list of x's going into the future. I don't care really about x. But you need to know these parameters in order to make the prediction. All right. So this is the learning process, right? Learning this list here is the parameter vector, is the point of w. So w, if you like, you could take it to be, for various reasons we kind of want it to be compact, so let's, I don't know, pick a large integer and make w this space. Okay, so our model, which is either f or the distribution star, they each determine each other, so it doesn't really matter which we think of as the model. But our model is parameterized by these three numbers, and the question is which three numbers reproduce the distribution that we see. Okay, are there any questions at this point?
Sorry to interrupt.
Yeah.
Okay, good. I'm a little confused what the measurements contain, because on the first slide I see that they're like XY pairs, but then I think you said like XT pairs or XG. I don't know if you misspoke at some point, but what are the measurements we're taking?
The measurements are XY pairs.
Okay, because if I imagine a pendulum moving, I can imagine getting different Y values, but
yeah, there's a bit of
the X value is,
there's a bit of an artificial component to this, which is that you only get one Y value at a particular time t. So somebody tells you, they give you a pair of numbers, 0.1 comma 0.2, and they say, okay, I released the pendulum at angular position 0.1, and then after some time, which is fixed, I use it for all the experiments, but I won't tell you what it is, that's capital T. It was at Y. But I only get that one position of the pendulum per experiment. And then I get another pair. I mean, if you like, I probably get many pairs with the same X, which would tell me, you know, they may not be the same because it's not deterministic, right? Because there's noise in the measurements. So even if you could get two pairs, 0.1 comma 0.2 and 0.1 comma 0.21, because you're sampling from a distribution due to the noise in measurement and, you know, other sources of noise. Does that make sense?
yeah. Why is X part of the measurement and not just like, because it's one of the parameters? Like,
Yeah.
why aren't the measurements just Y values?
Yeah, I think that's a good question. That's part of the story here that I probably could have done more clearly. Let's agree that there's a known distribution of X values. Like say they're uniformly sampled from. So let's say we agree that the experimental protocol is that X is uniformly sampled from, I don't know, minus pi on 4 to pi on 4 or something. So you get the samples, you know what the distribution of the X is going to be. So that's known. But you don't know, given X, what the distribution of Y's is, except from the samples, because you don't know the value of these parameters, lambda, g, and t. You'll notice the mass dropped out here, and that's because, as you know if you've done this calculation, the mass cancels out. So that's another part here that maybe could have been more elegantly presented, but really this model depends on these three parameters. Cool. second. Okay. So what do I want to say now? So here's a very interesting thing to notice. Look at the way that the parameters g and t appear in this formula. So the map from parameters, that is these triples, to models is not injective. I'll comment on the exact form of this non-injectivity in a moment, but let me just make this point with a diagram first. Well, someone tell me what's something I can do given a model. How can I change the parameters and not change the model?
You could increase t by like the period of that the pendulum is swinging.
Yeah, that's a good one. That too, yes. That's another source of non-injectivity. But what's one that actually interacts the parameters? Like do something to one parameter and something to another parameter and not change the model.
So make root g times t equal to constant.
Right. So I can double t and reduce root g by a factor of 2, that is reduce g by a factor of 4, and I won't change the model. Well, except I'll have to do something to lambda
What
as
about
well.
that? Yeah.
Okay. So I'll move back over to the first board and we'll discuss the exact form of this degeneracy. Or singularity. Okay. So what knowledge is to be gained from this experiment? Well, we want to know the true values of these three parameters. I'll call them lambda star, g star, and t star. But in the formula we just wrote down, so f if lambda star, g star, t star worked, i.e. the distribution of y values given x values for these parameters was exactly q, then so too would the following triple, or the following collection of triples. If I multiply lambda by a, g by a squared, and t by 1 on a for any positive a, all of those give the same model, right? So they're also true parameters. Okay, so which one is it then? Or maybe a better question is, who cares? They're all producing the same model. I chose the parameters, I chose the models. That's not out there in the world, right? So why should anybody care that there's more than one parameter which reproduces the truth? Does that have any actual significance? Okay, so let me plot W roughly speaking. So on one axis I'll put t, on another axis I'll put both lambda and g because they're scaling roughly the same, So here's W star, the or a true parameter. And here's a one-dimensional subset of also true parameters. So this direction is as a goes to 0, and this direction is as a goes to infinity. If you like, this kind of ends out here at 0, 0, infinity. Okay, so they're all true. Okay, so this is, I think, a pretty convincing example to show you that it's not weird to have a situation where multiple parameters, or remember these are our sort of, by algorithm here I mean this formula, right? I mean this formula is not synonymous with the function f. The function f is properly understood to just be the set of all input-output pairs computed by this formula. The formula itself is a means of computing that function. Okay, so we're identifying parameters with those formulas or algorithms. Multiple parameters determine the same model. So that's the first point I think it's important to understand. And by model, that's sort of a function or distribution, f or p. Now I'm writing it like this because I think a very important point here is actually the same point as the point in, say, theoretical computer science, that there's a distinction between algorithms and functions, and given a function there may be multiple algorithms which compute it. For example, there are multiple sorting algorithms that will put a list of integers in ascending order, or there are multiple algorithms for computing multiplication of integers, and so on. So given a function, there may be multiple ways of actually computing that function, sort of in practice, so to speak. And that's a kind of fundamental point, both in computer science and in learning. Okay. So this kind of model, where there may be multiple models and even sort of spaces of models, like there's a one parameter space here. This kind of model, where there are multiple models determining this, multiple parameters determining the true model, is called strictly singular. And this is the terminology of Sumio Watanabe, whose book Algebraic Geometry and Statistical Learning Theory is the primary reference for this seminar. And these kinds of models are what singular learning theory is about. The singularity here refers to the degeneracy, that is, the fact that there are multiple parameters determining the same model. Now, the main point I want you to get from this example is this is not a weird situation, right? You couldn't imagine a more simple system to measure in the world than a pendulum. You couldn't imagine a more canonical model than Newton's equations, and yet here we are. We have a strictly singular model. So, you know, if you think this is a weird thing, then you're wrong. Now, I want to get to the end of this by giving you at least a brief idea of why geometry might be relevant to learning theory and to singular learning theory in particular. So that's one thing I want to do. I also want to maybe give you some idea of why this singularity or degeneracy that I'm illustrating here matters, right? Maybe you could just say, well, fine, just somehow mix up these parameters. If there's not really 3 independent parameters, but something like 2, which is what's sort of indicated in this picture, right? Because you could imagine these sort of level sets, and maybe there aren't 3 independent parameters, but really only 2, sort of moving away from this locus, sort of perpendicular to it. And you could imagine that, well, maybe G and T aren't really independent, so I should just invent a single parameter that sort of encapsulates both of them. That's right, that is something you can do. But nonetheless, the fact that this degeneracy exists does in many examples, have a significance. It's not some mere phenomena that appears just in the mathematics we use to model things. It both appears in the mathematics we use to model things, but it also strongly affects things like the learning process, right? Because learning is not, it's not just a question of can you fit the model to the true distribution. The question of how you learn things and the nature of knowledge and how it gets used does depend on your model, and these singularities do affect that. That's one of the implications of Watanabe's work. Okay, so I want to quickly sketch that, and we'll spend the rest of the sessions developing all of this more formally and illustrating or proving that some of the things I'm asserting are true. Okay. So I want to go back and talk more about the learning process. So keep that example in your mind. So we get samples from this pendulum, and we're trying gradually to improve our estimates of what lambda, g, and t are. That is, we're sort of trying to get closer to this green line I drew in the plot, starting at some point in W far away from it, potentially. So as I said earlier, in practice we never know we may never know a true parameter to infinite precision. Perhaps you could look at that formula over there and solve it for lambda, g, and t, or maybe you do gradient descent to find values of lambda, g, and t that reproduce the measurements, or there's a bunch of other ways you might try and compute the true parameter. But if they're processes, if you're not just solving it analytically, if you're doing, say, gradient descent, well, maybe it never actually stops, right? There's some finite precision to your experiment, to your computation, and you can get better and better approximations to the true parameter. But in many cases, you'll never actually maybe know like the true value unless you happen to be able to solve it analytically. And the point I want to make is that the degeneracy or singularity, I'm not going to explain really what this word means today, right? Just think about it as being synonymous with the degeneracy, that is the lack of injectivity of that map. So this degeneracy in the mapping from parameters to models well, it affects the relationship between increasing precision, so getting more decimal places in your estimates of lambda star, g star, and t star, and I'll just call it decreasing energy. I don't mean energy of the pendulum, I mean kind of energy of the sort of process by which you're finding your true parameters. Or you could think about that as the loss if you're doing gradient descent, i.e. how close your predictions are to Q. So again, this will be something we define carefully later, but for now let me just say it like this. So you receive these measurements about Q from the environment, you've got a model. If you have some parameters in your model, you can use it to make predictions, and then you can compare them to the measurements you're getting from the true process. And then you have multiple ways, but you pick a way of comparing those predictions to the truth, right? The KL divergence, for example. But you have some numerical measure of how close your predictions are to Q, and you want to tweak your parameters so that that measure of closeness decreases. And that measure of closeness is what I mean by energy. Okay. So there are two things at play here. There are the precision of your estimate of the true parameter and how good is your current estimate. That is, how close are the predictions to the truth from the environment. Okay. So I'm just going to call this E. So that's the measure of how close the predictions are using W as your parameters. W stands for a triple lambda GT. Okay. Well, let's do a little calculation. So suppose for a moment that near this particular true parameter, and there may be more than one, E behaves like a quadratic form. I can hear background speaking. I think that's Billy probably. You want to mute? So suppose for a moment that near W star we have a formula like this. Alpha is just some parameter. We don't really care about it. But this is just to say that the energy has a bowl shape near the true parameter. So in particular, the search process, if it was gradient descent, would look something like a simple harmonic oscillator moving around in a potential well near W star. Maybe I'll draw that on the next board. Okay, so here's a picture of Billy will be sad if I don't use a straight line for that. So here's my energy, and here's the coordinate that indicates moving around in the space of parameters. Here's one true parameter. Here's another one. Okay, so let's call, so W star and W dagger are true parameters. We know more than one exists, just pick two of them. Well, I guess I'm conflating the general story with this particular example. Right now I'm talking in general, so this is really a story about any model, not this particular one with the pendulum. But okay, pick two true parameters. Now my assumption is that E looks something like a parabola there, but let's suppose it looks flatter than a parabola near W dagger. So this is sort of like x squared, and this might be like something like x to the 10. Right? If you zoom in between -1 and 1, higher powers of x look flatter. They approach a square well potential as the power goes to infinity. Okay, so here's W star. Let me put on this diagram the two things I talked about, precision and error. So here's zero error. Here's a little bit of error, E0 plus delta E. Now, why do I care about a little bit of error? Well, as I said, the search process is maybe actually what we mean by knowledge, not W star itself. So you can't ignore the process. And what does that process look like near W star? Well, it's a simple harmonic oscillator. It's going to, this is what I'm drawing here as a discrete approximation to a simple harmonic oscillator that you might get from doing something like gradient descent. Okay. Now if there's noise involved, then your search process, so if, say this is stochastic gradient descent, so you're getting samples from the environment and you're using them to look for W star, but there's some noise in the samples, so it's never going to be literally a simple harmonic oscillator. It's more like our pendulum, where it's being buffeted by small motions of the air and such things. Okay, so your search process is going to bounce around in here. And most of the time it will be below some energy level. But it will never maybe actually get to W star. So what does it mean to get an estimate of W star? Well, you could take the mean, for example, of all your positions of your simple harmonic oscillator. That would give you some estimate of W star. Okay, so that's one part of the story. The search process, the error, and now let me indicate on the diagram what I mean by precision. So precision is how close to W star. Well, it's a bit of a fiction to draw W star on this diagram, right? You don't know where W star is unless you can solve the system exactly. You don't even know that there's this bowl. All you see is the blue part, right? So you're looking at this blue part and you think, there's a bowl there and W star is kind of in the middle, but you don't literally know where W star is. Maybe you only have some idea that it's in this interval, right? So delta W is what I mean by the precision. Okay, that's the setup. Now, I want to give the relationship between delta W, which is a measure of the precision, and delta E, which is a measure of the temperature or the degree to which your approximation process is really sort of close to giving you a particular value. Okay, so by assumption, right, the energy at W star plus or minus delta W is approximately alpha squared times delta W squared. So this is delta E. Right, I drew these so that these meet. That's the, maybe that's not clear. That's the relationship between delta W and delta E. Right. Okay, so what does this simple calculation say? It says that if you want your estimates to sort of cluster more closely together, that is, you want to decrease delta W, so to halve the box containing W, or W star rather, well, you must decrease delta E by a factor of 4. Or to put it differently, to know the truth with twice the precision, you need to reduce the energy or loss by 4 times. And you might think about that as reducing the temperature of the room in which the pendulum is swinging. Right? So some work is required to do that. You do some work, you can get your approximation process to cluster more closely to the truth, and the difficulty is related to what factor you need to reduce the energy by. And in the case where near the truth the energy looks like a quadratic form, the factor is 4. Okay, I have one more diagram to draw, and I think I'm kind of on time. Are there any questions about this picture before I draw the more interesting one at W star?
Is this, this kind of reminds me of the very first meta-uni lecture we did. You were talking about like the power law or something. Is this, are these the two,
this is much...
is this the same concept here?
Well, I guess they're somewhat related, but I don't think it's fair to call them the same idea, no. Okay, I'll try and keep it on the same board, I guess. So let's suppose that near W dagger, the energy, the measure of how far away from the truth our distribution using the parameters W is, suppose it looks like x to the 2k. K here is some integer. Right? I just mean it's an even power of x, and I want the power to be a parameter. Well, doing the same calculation, that is thinking about some search process that's bouncing around here below with a given energy threshold, you do the same calculation, you'll find that in this case delta E is alpha squared delta W to the 2k. Right? Not surprising. Well, so what? Well, that means that halving the box, you have to reduce the energy by a factor of 2 to the k. Right? If you put a half over here, to cancel it, you need to put 1 over 2k over there. Well, it seems like a bad thing, right? It's harder to get your estimates to cluster around the truth. But you sort of need to stand on your head a bit and see that differently. Okay, so rather than thinking about it as being, I need to reduce the energy more to get my estimates, to get more decimal places in my estimates of W dagger, think about it like this. There are many parameters near W dagger that work just as well. That is, changing the parameter, like changing the 10th decimal place in the parameter, barely changes the model. Or maybe doesn't change it at all. The way I've drawn it here, the true parameter is isolated. We saw already in the example with the pendulum that the true parameter often is not isolated. You can make variations in the true parameter that literally don't change the model at all, not just don't change it much. Okay, so what's the significance of this bowl here at W dagger being flat? That is, there being many nearby parameters that don't change the model much. Well, the way to read that, or to understand it, is to think of it as saying that the truth is present at a more coarse-grained level at W dagger rather than at W star. Maybe I'll just erase here for a moment. So if you're near W dagger, you can use less decimal places, and it won't matter, right? That is, the model you're using is effectively using a less high or lower resolution version of Rn than you are if you're working at W star. So maybe I'll write this. The truth at W dagger is present at a more coarse-grained level. I.e., using less decimal places. So you need less bits to specify it. Well, the principle of Occam's Razor is that a simple solution is better. So you might expect that since, I mean, it's complicated. I don't want to pretend this is simple. Of course, if you want to actually write down both W star and W dagger you need the whole space, and you need to write down however many decimal places you need to write down. So when I say less bits, I mean locally. So locally near W dagger, a change in a model comparable to a similar one at W star that needs 10 bits to specify near W star may only need 5 bits near W dagger. So local changes can be specified with less bits. And so by Occam's Razor, you might expect the truth, W dagger, to be better a simple model is a better model, and a simple model is one that needs less bits to specify. And finally, this better is a direct result of the map from W to P being more singular or more degenerate near W dagger. If you think about the mapping from x to x squared is less degenerate than the mapping from x to x to the 2k. Maybe that's something we can discuss later. It's not meant to be immediately clear. You might think about the Weierstrass preparation theorem if you want to see the sense in which I mean that. Okay, so here's the storyline. Many models are singular. That is, there are multiple points in the space of parameters that determine the same model and determine the truth. That degeneracy matters because the learning process happens on the space of parameters, not out in the world. It's in your space of parameters. Maybe those parameters are the parameters that make up the neural network in your head or in your computer. So it's maybe in some sense made up, but it's how you learn. You learn in a machine, and a machine has numbers in it, and those numbers are the parameters. So the learning process happens on W, and the learning process is strongly affected by this degeneracy. And the way in which it's affected is that near some true parameters, the learning process behaves differently and has a different relation to information and the number of bits need to specify a solution than it does at other true parameters. So not all true parameters are created equal. Some are better by the Occam's Razor principle. And that betterness is related to the fact that the mapping from parameters to models is more degenerate near some true parameters than others. And all of this is what singular learning theory is about. So singular learning theory proves that much of what I'm saying is correct. Of course, I'm stating it in somewhat imprecise language, but you can prove that more singular true parameters generalize better. That's a theorem of Watanabe, which hopefully we'll prove. Okay, and this suggests a strong role for geometry in learning, because the nature of the singularity at W dagger is strongly related to the behavior of generalization of models that live near W dagger. And all of that is explained by Watanabe's theory. Okay, so the purpose of this seminar is to examine this link between algebraic geometry and the foundations of statistical learning theory, following Watanabe's book. And I think I'll stop there for questions. Thank you. I'm just seeing some questions in the chat. Okay. Mm-hmm. Is algebraic geometry a prerequisite? No. I mean, this material is going to get pretty technical pretty fast because it's difficult to avoid that. But in principle, you don't need to know any algebraic geometry.
I have a question about the parameter space.
Yep.
When we were talking about like having multiple possible true models like in the parameter space, and it sort of occurred to me that like maybe that only arises because you like chose too many interdependent variables to define. I don't know if it's possible in this case, but if we define the function f just in terms of a, then there would be a single true parameter, right?
That's right. Yeah. So you can change your model to eliminate these degeneracies. That's right. But then keep in mind that there's a trade-off there, right? So if you change your model in that way, it may no longer be the case that it's easy to. I mean, that may not be the model in which you actually want to learn. So the search process for the true parameter is its own thing, and it will work better with some parameterizations rather than others. So you can mod out, so to speak, by these degeneracies, but then you may not effectively be able to search on that quotient. And this is less subject to mathematical theory at the moment than the other part. It's hard to say what exactly I mean by that, but you could say the success of something like deep learning is a very good illustration of that. Deep learning models are wildly singular. So you might think, well, it would be much better to have a simpler, smaller parameter space which is less degenerate and search on that. But in practice, no. There are good reasons to search on a space which is larger, on which the mapping has more degeneracy. Maybe the search process can work better there. Exactly why that is remains a bit mysterious, but yeah, in principle, you can't always just eliminate the degeneracy by making these identifications. At least not without making something else more complicated.
I think there's also a practical answer to that, which is that the fact that you can see a non-degenerate parameterization relates to the fact that you already have knowledge of how the pendulum works. But if you are just a general kind of machine attempting to learn multiple things, like a deep learning model, you might not have that luxury.
Right. There's still the sort of like if you reduce this all to just the parameter a, like there's still the job of finding the correct value for a that you would still have to learn.
That's right.
Yeah, and also the property of being degenerate and also singular is a function also of what the truth is as well. So if you use this model to learn other truth, it might no longer be singular or degenerate.
Right. Thinking about, Dan, what you were saying about, for some reason,
sorry, but let me interrupt that question and just add something to your previous question, otherwise I'm going to forget. Sorry to interrupt you. I think it's worth paying attention to the meaning of the parameters in this model. These aren't just randomly chosen parameters, right? When you are studying a pendulum, there is gravity, and the coefficient g is completely different to the parameter t that relates to how long you paused before you took the measurement. They're independent factors. Now, when you have a model in which they are independent factors, you have singularities. You could change the model to mix the two. Physically, that would be nonsense, right? To consider root gt as like being some fundamental physical thing doesn't make any sense. But you could do it statistically. It could be a single parameter in your model. But then actually you're not modeling the real world very well, because somebody could change t, or the variations in t have a completely different origin to variations in g. So if your true distribution were to change, you would be completely screwed if you mixed root g and t. You would be completely confused by a small change in t. You would think maybe you couldn't tell that apart from a change in gravity. Whereas if the parameters are independent, and actually their own degrees of freedom, then there are changes in the true parameter which you would be able to understand as being actually independent. So there's a sense in which the real world does have independent degrees of freedom that you can't just identify them or quotient out by relations between them in the mathematics without paying a price somewhere. Okay, so that's the point I want to make about that. But what was your other question?
I'll just reserve that question, and I've got a question in reply to what you just said.
Mm-hmm.
I then wonder how I imagine in many contexts you have a problem to solve and you sort of understand all of the variables that probably determine what the model should be, and then so it's clear what the parameter space should be. But I wonder all of this process of doing learning here seems like first you have to figure out what the right parameter space is, and then you do learning. Is there any theory of figuring out the right parameters to use, or changing parameters, adding or eliminating parameters?
Adding or eliminating parameters is a more subtle thing, I guess, but model selection, which model you should choose, is a big part of statistics. And the tools we're discussing provide means of, in principle, making those choices, right? If I were to say, should I take a model with 100 parameters in this particular form, or a different model with 10 parameters in this form, there are principled means of answering that question. I mean, maybe in practice you can't actually compute the answers, but the principled comparisons exist. I don't know if you want to add to that, Edmund.
So model selection is definitely what we'll be looking. We'll look into model selection using singular learning theory, as well as the usual statistics way of saying whether or not less. For example, the Bayesian information criterion is kind of a usual way of trading off more parameters versus how accurate your model is at the moment with certain parameters, for example. So yeah, that's definitely a concern of statistics.
I mean, you could say that.
And you might.
Go ahead.
I was just going to say that one way of thinking about it might be that singular models sort of give you flexibility in the parameter space, is maybe a word you could use. So a priori, you don't necessarily know whether a 10 parameter model or a 100 parameter model is going to best model your truth, and the singular structure sort of allows that search process to happen across that span of different number of parameter models, which is not the case in regular models.
Mm-hmm. Yeah.
So my reserved question was, you were talking about, I was for context, I was talking about what about the parameter space that's just one dimensional, and you were saying that learning tends to happen better on this sort of three-dimensional parameter space than that one-dimensional space.
Mm-hmm.
Is that somewhat because with more dimensions you can sort of move around off the degeneracy or the singularity, I don't know what you call it, but if you were if the only degree of freedom was moving along the line, I don't know, it strikes me as intuitive that being able to move off the line and around in different dimensions would sort of allow you to take more paths, to have more paths available to get to these to like a true parameter model.
Yeah, I guess I might have some intuition like that, but it's very hard to. I don't know that I can really give any story like that that is not just mere what. Yeah, right. So I don't really. I guess there are many stories like that you might tell. I don't know anything really convincing that I can tell to you which explains, like in some simple way, why having more parameters might be better. I will say something like this, which is that you could just artificially make your model more singular, right? I mean, we could have in our model t prime, and instead of t, put tt prime there, right? Add a parameter and just put in the product. That'd be more singular, but you would be surprised if that really helped you any, right? Now that's because the model you're taking there is more singular than the truth in some artificial way, right? The truth is that formula, more so than it is the function. The truth is the actual generative process of physics, right? Physics really has, so we think, gravity in it and time, and those are different things sometimes. And so that formula is sort of actually what is going on. And if you choose a model which is artificially more singular than what is really going on, maybe it doesn't help. So you can't just add parameters and sort of expect to magically do smarter things. I guess Skarm was asking a similar question in the chat. However, many real-world phenomena are way more complicated than any model you'll ever write down, say English language. And that's part of the reason why just adding insane numbers of parameters to deep learning models, you never quite overshoot like that. You don't have to be worried about overshooting and making your model more complicated than reality. Reality is more complicated than any model you'll be able to compute with in your data center, so don't worry about that. So in some sense, you can expect in some regimes that merely adding parameters and making, therefore, your models probably more singular, but maybe not, might help. But the storyline for why that is, we can tell you the mathematics, which says, to some degree, why it is, but the storyline sort of, hinges on a deep understanding of resolution of singularities or something. So it's not trivial to explain, and I don't think I can do it. I mean,
I also want to add that. Sorry.
Yeah, go ahead.
I just also want to add that in the kind of the practical case, I think I'm getting more and more the sense that the unrealizability case is the more typical case when we are studying
Right.
real-world phenomena, and hence sort of adding possibilities of lowering that lowest that closest approximation to the truth is going to get better unless your added parameters only introduce degeneracy in sort of higher level sets, not the lowest one or something like that.
Yeah.
Sorry, that I'm also just going to erase one of the board and start writing.
Yeah, good. Yeah. So we have a supplementary session coming up in 10 minutes, I guess. So Edmund is going to present, well, you can say what he's going to present, but some more mathematics as opposed to this kind of story time.
Right. I guess the preview will be that then I think I vert a bit from the plan, but I'm still going to talk about the Fisher information matrix, but I'm going to talk about it via sort of an example and illustrating sort of a lot of what you were saying just now with like common statistical practice, and it's a regular model for now. It's a quite complete model, and introduce model selections and Fisher information matrix and etc. via that.
Cool. Yes.
Dumb question. How do you use the eraser?
Yeah, you should click the eraser and then click and drag.